Hello and welcome back to the course on statistics. Today we're talking about the t-test. It's been a long time coming and finally it's here and we're all prepared because we've talked about the t-distribution and also we have all that knowledge about the standard hypothesis testing that we've been doing for so long. So we will definitely know what is going on when we're starting the t-test. So let's have a look. Here's our challenge. It is recommended to walk 10,000 steps a day to be healthy. You are wondering if on average Americans are meeting this recommendation. You surveyed 10 random people about how many steps each of them takes per day on average and got the following responses: 7,900, 8,200, 11,350, and so on. It's evident that within your sample, on average, respondents are taking less than 10,000 steps. But can you infer the same results for the whole population of America? Very interesting question, very interesting challenge. And yeah, so basically, one thing I wanted to point out here is that you'll see, what will you see? This on average. And on average, and that where they're coming from is that it is recommended to walk 10,000 steps a day to be healthy. That's assumed, like implied on average. Obviously, sometimes there'll be days when you walk less, sometimes you'll walk days when you'll walk more. So 10,000 means on average per day. And that's why this average is popping up, that 10 random people, how many steps they take per day on average, meaning like in a week, how many steps do they take on average per day, or in a month, or in a year. And same thing here. So this average, what I'm trying to say here is that this average has nothing to do with our means, our standard deviations, and so on. It's just the way the parameter is constructed. So it could have been, we could have just had a parameter where it's recommended to walk this many steps per year, right? So what would it be? 3,650,000 steps, 3,650,000 steps per year. But we don't have that. We have per day, so that's why this extra average is popping up. But don't let it confuse you or get you off the track. We know what we're supposed to do in terms of the t-test, and we're going to stick to that. And the parameter can be whatever it needs to be. So let's just copy the important information here, and let's state our hypotheses. So our null hypothesis is that the number of steps is at least met. So we want to prove that we can see that it's from here. We can just see that there's only 2 people with over 10,000. That means the mean is going to be less than 10,000. So we want to prove that it's less than 10,000 for the whole population. And as we discussed before, we need to assume a null hypothesis, which we're going to try to get to a contradiction, and then therefore we'll be able to reject it, and therefore the only alternative will be possible. So what you want to prove should always be your alternative hypothesis, and here we want to prove that the number of steps is not met, meaning that it's less than 1,000, just like as we see here, and therefore our null hypothesis is that it is at least met, so people in America on average take 10,000 or more steps per day, and our alternative is and hopefully we'll be able to reject the null and keep the alternative, is that they take less than 10,000 steps per day. And what's interesting here, well, first of all, I hope that now you're more comfortable with this logic after we've discussed what it means that you cannot reject the null hypothesis previously, and about the contradictions, and about what happens with the null, and when we reject the null, we keep the only possible alternative, and so on. So hopefully you're getting more comfortable with that logic, and remember to practice that intuition behind everything we're doing. But the other thing I wanted to point out is that it's pretty cool. It's a pretty cool notion that you can just take 10 people, survey them, and find out something about the whole of population of America. And you don't have to, or whatever country you live in, you don't have to survey more than that. Or as you'll see, we'll be able to derive some insights from already 10. And it might be a bit of a hard to believe concept, especially if you think of it in the way that, oh, well, I'll just go out and I'll survey my parents, my siblings, my children, my friends, and I'll definitely get 10 people. And there's no way that is going to be representative of the whole of America. Well, that is true. That is correct. But the thing there is that sample isn't random. That sample is your family and friends. And we're talking about a random sample. And even more so, if you just go outside on the street and you survey 10 people, that sample isn't random either, because those are people who live in your neighborhood. Those are people who live in your street. And maybe you'll be able to infer something about the people who live in your street but you definitely won't be able to infer something about the population of America because that's just not a random sample. And as we remember, the assumption is, one of the assumptions is that it's a random sample. It's very important to make sure the sample is selected at random, and it's much harder to select a random sample from the whole of the population of America. Even if you were able to do that, then you'd have to like fly to their location or call them up, or how would you even select that random sample? You need to have all of the information on all of these people. But as long as you can select a random sample somehow, then like somehow magically, then this is a pretty cool notion that 10 can be even 10 can be enough because we have the t-test. So that's a quick comment on the sample there. And the other thing that you can see here is that this distribution has wider tails this time. So usually our tails go down to the bottom pretty quickly. Now they're pretty wide, and that's because what we talked before, this is a t-distribution. It's not a standard, or it's not a normal distribution. This is a t-distribution for the t-statistic. And the key point here as well is that it's the t-statistic. So as you can see, once we draw these, we're not putting the mu x bar or the sigma x bar or p bar, the x bar in this case. We're not putting all of those. We're actually putting a 0 here because we're going to be looking at the distribution of the t-statistic. Remember, like we were calculating the z-score, and we were saying that the z parameter or z-statistic has its own distribution, which is centered around 0 and has standard deviation of 1. Well, a t-statistic has its own distribution as well, and that's exactly what's going on with it. And because we are constructing a t-distribution, we're just going to do the inferences for the t-distribution here, or from the t-distribution, rather than from the original sampling distribution. And you'll see exactly why when we talk about the t-table. So for now, let's just say this is the t-distribution. It's derived in the same way. So it comes from the sampling distribution. So the central limit theorem still holds. It's just going to be easier for us to deal with the t-distribution rather than plotting the original sampling distribution. So this is the derived t-distribution, which we're going to derive just now. All right, so let's do this. As we discussed some time ago, now the best way for us to reject the null hypothesis, like the strongest assumption we can make, is that from here that mu is actually equal to 10,000. We want to prove that it's less than 10,000 based on this data. If we were to select mu, for instance, it could be anywhere. We could select it at 15,000, but it's going to be a weaker proof than if we selected at 10,000. So we want the strongest proof ever, and that's why we're going to select 10,000. Then we're going to say, we're going to calculate. Now the thing here is we don't know anything about the population. Usually we at least know the standard deviation or some parameters of the population. Here we don't know anything. We don't even have any data on that. What we do know is our data set here, so we can calculate the standard deviation in our data set. And as you remember, for samples, we don't use sigma, we use S. So there we go. So that's S, that's our sample standard deviation. And bear in mind, it has nothing to do with the sampling distribution, because for the sampling distribution, we have sigma x bar or sigma p bar. This is S. This is just for this one sample. We have one sample. You can write it out. I actually did this in Excel, so it might contain errors. Hopefully not. So you can see that mu is for the population. That's our assumption. That's the only thing we don't actually know it about the population, then we're assuming it about the population. Then S is the standard deviation of our sample. So you can just take these, put these in Excel or into a calculator, and based on the formula we discussed at the start of the course, you can calculate the sample standard deviation. And then X bar is 8595. That's the mean of your sample. Basically, that's the mean of your sample. And as you can see, we're not using mu here. We're not using mu x bar or anything. This is not the sampling distribution mean. This is just the mean of your one sample that you picked out. Normally, we don't calculate these things. That's important to remember. Normally, we don't do calculations about the sample or anything. We just straight away proceed to the sampling distribution. But in this case, because we don't know that much about the population, we have to make inferences about the population. In fact, we're just going to be using the T-statistic is going to do all of that for us. We don't have to make inferences about the population from the sample and then do all the standard process. We're just going to use the T-statistic, and is going to do all of the, is going to have all of that groundwork built into the formula. Speaking of which, here's the formula. So the T-statistic formula is very similar to the Z-statistic. You can see that it's an adjusted version of the Z-statistic. So here we've got X bar, bam, put it in. mu, which is we're exactly same. But in the Z statistic though, we are calculating from the sampling distribution. So that'll be mu x bar minus mu. Here it's x bar minus mu. So that's why we said we're going to be dealing with the T distribution rather than the sampling distribution over here. Because that's the way we're calculating. That's the way we're structuring the calculations, the formulas that we're using, and we are applying the T distribution. There we go. At the bottom, we've got S divided by square root of number of degrees of freedom. S is the sample standard deviation. Done. Put it in. Nu is a number of degrees of freedom. It's always just the number of samples minus 1. That's just the way it's calculated. And voila, 8.595 minus 10,000 divided so on. It gives us minus 2.95. So let's plot this T value. So here we know like this is 0. So these are already standard deviations. This is just like as in the normal hypothesis testing, that the ones that we've been doing, it would be the same as if we were plotting the Z statistic. That's what it would mean. And we're pretty much doing that. We're just kind of like mixing in the sampling distribution chart and the Z statistic together because it was very intuitive. Here we're just going to plot this T now. There we go. T minus 2.95. So 1 standard deviation, 2 standard deviations, boom, 0.95 standard deviations over here. And now we need to find out. So if we want to reject the null hypothesis with a 95% confidence, now we just need to find our critical T value. So I'll just show you the T table now and you'll see what I mean. So here's the T table. As you can see, it's actually smaller than the Z table, than the Z score. But at the same time, that is only because they shrunk it to make it legible. That if you were to have all of the possible values here, it would explode. It would be huge because of the extra variable that we have, the degrees of freedom. So now you don't have that luxury of actually just looking up a Z value and then finding out the probability. In fact, this T table works just like when we were talking about rejection regions. So remember when we said there's a second way to use the Z table, Z score, when you can just look up a critical Z score from your table, so kind of like reverse engineer your table and plot that critical score, Z score, and then compare your Z score to the critical Z score for that degree of certainty that you want. Well, that's exactly how the T tables work. They don't work in the normal way that we did, what we originally discussed for the Z tables. You cannot, based on a T value, you cannot just pick out the probability for that T value. It works the other way. So you say what level of confidence you want. So in our case, we want T 95. We want 95% confidence that our result is correct, or that we want to reject the null hypothesis with a 95% confidence if we can. And then what we do is we go down. So we're doing the one-tail test. So 95. So that means there's 5%. We need to find the area with a 5% chance of our observation or our sample falling in there. And so now basically we look for our degrees of freedom. In our case, we have, how many do we have? It was 9 degrees of freedom. So we scroll down. So 9 degrees of freedom. There it is. That's our 9 degrees of freedom. At a 95% confidence interval at 9 degrees of freedom, the T critical is 1.833. And that's all we have to know. So we put this into our calculations. T critical at 95 degrees confidence and 9 degrees of freedom is minus 1.833. So the thing about T tables that we need to know is the way they're set up is the T table gives you, so this is the critical value. So for 95% confidence and 9 degrees of freedom, this is the critical value that's on the right here. So for instance, it would be somewhere here, 1.833. And basically, so that's 1.83, it's sitting over here. So that means that anything to the right of the critical value, you reject. That's the way the T tables are set up. So whatever value you see, that means if you're testing the right tail over here, then you reject it if it's greater than the critical value. But because the T distribution is symmetrical, that means you can just symmetrically look at it over here, meaning that our T critical, because we're dealing with the left tail, is minus 1.833. So it's actually somewhere over here. That's our T critical. And therefore we reject anything to the left. As you can see, our value falls to the left, so T is less than T critical, it falls into this rejection tail. And yeah, that basically means that in our case, we can reject the null hypothesis. And therefore, so we've come to a contradiction. We've basically, what this is saying is that it is so unlikely, if this were true, that on average in America, people were taking more than 10,000 steps or more per day, then this is what the distribution we would have. And it would be so unlikely for us to pick out this random sample, this random sample of these parameters that we've calculated. It would be so unlikely that we can, with a 95% degree of confidence, reject the null hypothesis. And therefore, so we've come to a contradiction that it's so unlikely. We can reject the null hypothesis, and therefore the only possible alternative is the alternative hypothesis, where they're taking less than 10,000 steps. And what I wanted to point out here is that, as you can see, the tails are thicker here. Well, this is just a visualization, but what this means is that tails are thicker here, and the distribution actually allows for values to go further away. And we discussed this, that the distribution allows for values to go further away. And it's just the way that we've drawn it, and also based on the parameters that we've calculated, that in this case, we've still found a sample that doesn't conform to this distribution, and therefore this distribution cannot be the true case. And the reason for that is that you can see just even from the sample that a lot of the people here are taking way less than 10,000 steps, 6,000, 6,000, and so on. That if this is a random sample, it would be very unlikely, given this distribution, it would be very unlikely to pick out this random sample, even in a t-test, not just a z-test, but even in a t-test, which is even harder to prove, which allows for more variation in your data, for more values to be in the tails. It still is not something that is plausible, and we're rejecting this null hypothesis. So there we go. I hope this clarifies up what a t-test is and how to apply it. As you can see, it's a very similar process. We just calculate a t-statistic instead of a z-statistic, and then we compare it to the critical t-statistic for that level of confidence we want and the number of degrees of freedom. And by the way, if you look at the table, so if you look at this table, you'll see that what happens when you increase the degrees of freedom, you can see that the values change at the start, so they change rapidly, quite a lot, but then they start to change slower and slower and slower. So when you get to 30, you can see that the values are barely changing at all. And that's why after 30, this table specifically, it skips, it goes to 40, to 60, because just to show us that, what is it converging to? That's your Z statistic over there, you can see. So it's like pretty much becomes Z statistic already after 30, 1697, 1645, no big change happening after 30. And that's what we mean, that after 30 degrees of freedom, there's no much point in using a t-table or t-statistic. You can just use a z-statistic approach as before. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.